So what I'm going to talk about is, or mostly explained in this paper, which came out like about a year and a half ago with my student, well, actually former student. He just graduated, just got his PhD, and is heading to Institute for Advanced Study. So this is, what I'm going to talk about is more like mathematical physics or math. So the main results are completely rigorous, but I'm going to spend a substantial portion of the first lecture in explaining the motivation. So don't worry too much about the words being fuzzy or not even have any meaning to a mathematician, because later I'll try, it's all motivation, purely for motivation, and the things which I want to explain later are actually going to be can be defined precisely. But anyway, so so the story in general has to do with well, special phases of quantum matter, which are called gapped, or sometimes topological, which is, I think, is a bad name, because it's topological. Well, the relation with topology is completely unclear at this stage. Well, not completely clear. So, and the phases of matter, well, what is that? Well, going back to like the 60s, it was realized that to define notion of a phase of matter, well, at zero temperature, positive temperature, you need to work with infinite volume systems, which is, only there, in infinite thermodynamic limit, the notion of a phase becomes sharp. And therefore, you have to work, within the world of C-star algebra, states on C-star algebra, stuff like that. So it's basically a subject, a chapter in operator algebras. On the other hand, there is also some belief among physicists that this particular kind of quantum phases of matter is related to a rather different physical problem, namely topological quantum field theory. And here topological is without quotes. Sorry?
In what dimension?
In any dimension. It all happens in all dimensions. So I'll remind you later what these things are, but roughly, because there's no completely, well, at least here there's no completely satisfactory definition. But they live in very different worlds. So here you have functional analysis, operator algebras, and here you have some topology and maybe category theory. And what somehow, so this connection is not very clear, but it turns out that in some, well, you can connect them in some way by means of homotopy theory. Okay. And I'll spend most of the lectures entirely on this side. I'm trying to define precisely what it means, what is a phase of matter, and what one can say about them, try to classify them, or at least identify any invariants of a phase. But the motivation, much of the motivation comes from this side, so which is not completely rigorous, but I'll explain that motivation today. So, but anyway, so at a very rough level, still I need to say what I mean by gapped phase of matter, and I'll explain later, probably maybe later today, maybe in the next lecture, what exactly I mean by gapped phase of matter. But it's at some very rough physical level. So, so first of all, a phase of matter. Okay. Well, actually, there's some, I would say, also deformation theory in some way. Okay. So, and then, so what's the first of all phase of matter? Well, it's equivalence class of physical systems in infinite volume. Well, equivalence under what? Well, I'll again discuss it later, but at least physically, equivalence means, qualitatively, the behavior is the same for all systems in the equivalence class, whatever that means.
You need to know what a system means?
Yeah, system, I can say now a system in the traditional approach, which goes back to the 60s, it's a pair well, actually maybe triple. It's what's called C-star dynamical system of a particular kind. So you have some C-star algebra, not completely general one. There's, well, I'm going to care about some large class of C-star algebras, which are very simple C-star algebras. You just take, I think, called uniformly hyperfinite C-star algebras. So we basically take infinite product of matrix algebras and complete with respect to some natural norm.
So it's not usual phase of matter like liquid, gas, solid, and something?
Well, those can be formed in this framework. This framework, the traditional framework applies to, actually it was mostly used for non-zero temperature. And liquid, solid, they all like fit in here too.
So there is some algebra or whatever?
Well, I mean, in the simplest situation, well, the different setups, but the types of like an Ising models where you have typically just some sort of set of points in Euclidean space, maybe hypercubic lattice, maybe just some Delaunay set, and then you just attach a matrix algebra, finite matrix algebra to every point, just take product over all points, and complete to get a C-star algebra. So that's
two-dimensional systems, basically.
In general, d dimensions. Okay, so, and lots of results are known about such systems at positive temperature, but more recently people focus on zero temperature also. So, so you have this algebra, you have a state. I'll remind you later what a state is for those who don't know, but just some positive linear function. And then there is also some evolution, some one-parameter group of automorphisms. Let's say evolution, or Hamiltonian, or something like that. So that's sort of roughly what system is. Well, let's say evolution, we should say Hamiltonian. And Hamiltonian acts in some Hilbert space attached to this pair via the GNS, Gelfand-Nymark circular construction. And the word gapped, in the gapped, so gapped means the following, that, let's see. So means that so unique, so there is a unique state with eigenvalue 0 and the spectrum of H is this point. It was contained in here for some delta greater than 0. So like there's a unique ground state, and well, Hamiltonian is usually positive definite in this setup at zero temperature, and any excitation costs you finite energy, positive energy greater than some delta. So this gap is referred to as the gap between the zero eigenvalue and the next in the lower border of the spectrum.
The infinite volume is correct in the algebra, right?
Sorry?
The notion of infinite volume is just given by the algebra, right?
Yeah, infinite volume just means you take a product of infinite number of matrix algebras. That's what infinite volume.
So that's there is no measure, right?
There's no
measure on volume.
Measure on what?
I mean, the notion of volume needs to exist, right?
Well, there's no volume. Metric, I mean.
I say infinite volume, right?
Yeah.
So there is no volume per se.
Yeah, there's no volume, yeah.
Could you replace it by infinite number of degrees of freedom?
Well, it is infinite already, because like infinite product of finite number of degrees of freedom is still infinite, right? There are continuum models of the same sort. Like you can also consider particles moving in the continuum. This is like a system of spins at each point on the lattice, and you can also consider more realistic models involve particles moving in space, but these are much harder to discuss. So the only book which tries to deal with them systematically, there's David Royal's book, which deals with both lattice and continuum systems, and you can see that a lot less can be said about continuum systems in any case. So for lattice system, there's a very nice book by Barry Simon, which explains a lot of what's known about the lattice system. That's where the standard goes-to source, called Statistical Mechanics of Lattice Gases.
So speaking of physical applications, it's not a gas, it's not a liquid, because they are not gapped, right?
Well, you can say it's incompressible liquid. Like
well, you can move the liquid, and then the energy, well,
well, this thing cannot move continuously, so it's basically like a spin system. That's a like Ising type model or something like that.
So, but not usual water. Water is not a gap.
Yeah, although actually the theory of phase transitions is much better developed for, like, for example, a book of Simons called Lattice gases, because one very crude approximation is to replace like a gas with a spin system, and qualitative behaves actually the same. Nobody understands why, but people model sometimes gas and liquids by saying, well, you have particles which can jump from point to point on the lattice, and that's some crude approximation to actual gas or liquid. So that also. So it's believed that not much is changed if you move to continuum system, but actually that's very hard dealing with continuum systems. That's why I stick with this type of systems, lattice systems. Okay, so now it turns out that this gap systems have actually a lot more structure than generic ones, and we're going to be making use of it repeatedly. Now, okay, what's equivalence class? Well, it's hard to define for now, but at least one thing is clear. What is sort of an example of a trivial equivalence class? So, well, trivial system. They probably well, the algebras can all the same. Just let's say we have hypercubic lattice in the dimensions, and some product, and each aj, which has operators on a finite dimensional Hilbert space, incomplete. That never changes, but you can take omega, the state, which is the tensor product roughly, basically over J of sort of states on individual algebras, and take that to be a pure state, each of these guys. It's a really boring system where basically different sides of the lattice are not entangled in any way. So that's a trivial sort of, people say, pattern of entanglement. And the name of the game is to figure out some way to distinguish different patterns of entanglement, this being the trivial one. So there's nothing else available really at zero temperature. And by the way, this Hamiltonian, it will turn out that's actually not very important. The important thing, it exists and has some, and reasonably nice, but it doesn't really matter what it is. Okay. Now, the invariant is going to be a invariant of a wave function over a state for which it's known that some nice h exists, but the construction is not going to use explicit form of an invariant. It doesn't matter, because the point is, you can ask, okay, how many, if you fix a state, how many Hamiltonians with its properties exist? And the set of such Hamiltonians is actually contractible, it's actually a convex set. So from point of view of deformation theory, you can just forget that they're there. You just homotopy equivalent to a point, so you can just, it doesn't matter what they are then. So that's the ideology. Okay, so just to make sure that we're not talking about something totally unphysical, some examples of gapped phases or gapped states, which are non-trivial. Okay, so actually the historically first example is integer quantum Hall phases. So what is this? Well, it was discovered about 1980, I think, or 81, that in some sort of quasi two-dimensional materials, so here's a slab of some two-dimensional material, well, in magnetic field, some two-dimensional electron gas with perpendicular magnetic field, if you apply some electric field in this direction, or if you wish voltage, like put a battery here, like between this and that edge, then current flows perpendicular direction. So this is the y direction, this x. Now by itself, nothing special about that. That always happens when you have a magnetic field. But what's special is that this material is actually insulating at zero temperature. And therefore, nothing flows in this direction. There's no dissipation. But the current flows in that direction. There's no entropy production because perpendicular motion. And moreover, the most important thing is that the current, of course, proportional to the electric field. And the coefficient is quantized in some units, correct units. Well, standard notation convention is that this is actually integer with extremely good accuracy. Such a good accuracy that, in fact, now that it's used as a standard of electric charge or something like that. So basically, yeah, this is the best way to, I think, or establish some standards for electric charge or resistance. So now, and by the way, if you decide to apply voltage this way, then you'll find that the current in the perpendicular direction with like this. So this effect is kind of parity odd, or okay. So it depends on switches sign under change of orientation. Okay. So now, well, and later, a few years later, we discovered that in some, at even low temperatures and stronger fields, you have some, basically the same thing happens, but sometimes you'll see that actually these phases might have also fractional values of this 2 pi sigma h. So you have these phases. So, and from modern point of view, this its stability, the fact it's kind of frozen at some value, is because there's some numerical invariance of phase. As you deform, say, change magnetic field, then nothing qualitatively changes, and the phase is the same. And because this is actually invariant of a phase, it stays the same too. So one of the goals of the subject, the long-standing goal, is to explain why. Well, first of all, why is it so robust? And second, why it takes particular values. For example, it takes particular rational numbers, or sometimes integers. So these are non-trivial examples of non-trivial phases. Okay. So, so let me now describe the other side of the story, this TQFT, and which at first sight has nothing to do with this, with anything here, because topological field theory is a well, let's actually discuss what topological field theory. So first, what is TQFT? Well, I mean, very roughly, from a physical standpoint, they were originally defined as any quantum field theory which, independent of the metric, or more precisely, with the property that stress energy tensor, which is some factor, I don't remember, is derivative of the action with respect to the metric, is, well, on classical level, you say that this is a proportion to identity operator, or identity observable, times some function of this metric, maybe some other fields, background field. So that's what topological field theory means, but roughly independent of the metric. But that's a very unclear definition, and there were many attempts to improve on it. So there are Atia's axioms, which said that TQFT is a functor from some category to some other category. So TQFT in D dimension in D spatial dimension. Meaning D spatial in one time, is a functor from some category of boardisms whose objects are compact, closed D manifolds. And morphisms are from the name of that boardisms between closed D manifolds with D plus one dimensional manifolds. So functor from this category to just category of finite dimensional vector spaces or complex ones.
Sorry, in the first definition, T mu is equal to what? I just don't see.
What?
T mu is equal to what in the first definition?
I can't figure.
You gave a definition that the energy momentum tensor is equal to something, and I don't see from here what is this something.
It's something is identity. Time. So basically you can say 0, but if it's not 0, it's identity. Doesn't depend on the fields and the theory.
Well, that conforms to other definition that there is no spectrum of the Hamiltonian, right? T mu, so it's...
Well, basically, one of the implications is that Hamiltonian is just 0.
Hamiltonian is 0, yes. Okay.
So in practice, it's not quite 0, but it's basically some constant which depends on the geometry of your space. It doesn't depend on the dynamics.
In flat space it's 0.
In flat space it's 0, but in general it might depend on curvature. Yeah. But that's okay. So modern definition involves these functors. The most naive one is like this one by Tia. Now that's not very useful in the sense that it's not clear how to, first of all, it doesn't capture all locality which is inherent in field theory, because you have some global object. It's not very much information on these guys. But there is an improvement. Well, you want to refine this category to some n category, or d category.
So what was wrong with this Atia's definition?
Well, it just doesn't have enough information. It's like, that's, of course, field theory is supposed to do this for you, should give you a functor. But it's a lot more other things you have to do. For example, there's no locality in, you're supposed to say something that if you cut your d-dimensional space, there's still locality. You can be able to cut it. It's currently not captured in this definition at all. You need to have some extra structure. Otherwise, just too many of such guys. Okay. So functor. Well, actually, it should be some not just functor, but symmetric monoidal functor. There's a symmetric monoidal category. And this is also symmetric monoidal. Should be symmetric monoidal functor. So here you can just improve this guy from a D category. Whose objects the morphisms category becomes dimorphisms here, and objects here are just points, and morphisms into points are just some one-dimensional manifolds, and then morphisms are like this, some sort of films and so forth. Okay, so that's better, but then you have a problem. Then this is just you need to choose some D category here. And there's no obvious choice. So what is the physically motivated choice of a symmetric monoidal D category? I don't know one. So now also D category is not quite convenient motion to work with. So it was proposed that the D infinity category is better. So the best definition so far is have a functor, symmetric monoidal functor in D infinity category of bordisms, when you also add some higher invertible morphisms to some unknown D infinity category here, which is somehow related to this. So there's not, again, physically motivated choice. So that's a bit of a not really a definition. Okay.
I'm not sure how many people in the room, at least in the physics part, know what the D infinity category is.
It doesn't matter because no one will use it. So just all for motivation. So I don't know myself what is D infinity category. I barely mentioned this about one infinity categories, but D infinity, D greater than 1, I don't really know. So anyway, but okay, so physicists don't know what D infinity categories are either.
And so D is K, it's not the same D as the dimension.
It's like the eraser.
Okay. There we go. So, what do you think?
D in the category is an integer K. It's not the same as dimension.
Yeah, dimensional space. Yeah.
It's dimensional space?
Yeah. So you have D spatial and one-time dimension, so we're going to have D infinity category in principle. Okay. So physicists, of course, have their own way to produce examples, at least, of TQFTs, and that's by writing some action classical field theory, then quantizing it. And there are some examples which have been constructed over the years. And for example, the key point is that at some point people realized that these two examples describe some of their properties described very nicely by some very simple topological field theories. So that's why the subject actually, why it became connected in some way. So so how do we describe this very simple fact in terms of some sort of TQFT? Well, that's really kind of baby version of TQFT. So first of all, this particular TQFT has no degrees of freedom whatsoever. So what is there? So there is normally in field theory you have some sort of path integral of some fields. Here there's nothing. You don't integrate at all. So that means you have basically classical, just action. That's it. And the action doesn't depend on any dynamical field. It depends on this electric field that you have there, no magnetic field. So what sort of action has this produces the right thing? Well, if you write an action which is just a function of some background fields, so well, what are the background fields? Well, electric and magnetic fields are just components of a closed two-form, and this two-form is just the curvature of some connection on principal U1 bundle, which I'll schematically write as a locally defined one form. And the action that people write down is like this. And now it's integration over 3 manifold, which is physically should be just some two-dimensional manifold times time. So, and of course in real life, the bundle where a mu, on which a mu is a connection is never non-trivial. It's always trivial. There are no magnetic monopoles, and that's why there are no non-trivial bundles to consider. But as a purely mental exercise, we can consider a situation when A is a connection non-trivial U1 bundle. And then it turns out this action is, well, this is not a globally defined one form, so we need to interpret this appropriately. It turns out the interpretation exists only if K is an integer. So on the other hand, if you compute the current, well, the current is computed as a variation of this action with respect to the gauge field, and you'll discover that, well, some formula like this, where this completely symmetric tensor with 3 indices. So, and if you just compare to that, you'll see that this K is simply 2 pi times sigma whole.
Could you repeat again? Why K should be integer?
Okay, so if A is just a one form, there's no reason for it to be integer. But if you believe that the action should be well defined even when A is a connection on principal U1 bundle, then you can say, well, maybe one way to interpret it, which is due to Witten, is to say that maybe I, first of all, extend my manifold, and also general 3 manifold. Maybe I realize my closed 3 manifold is a boundary of some 4 manifold, and I extend my U1 bundle to the whole 4 manifold, and then I can write this as a this. Now, it's possible to show that for this particular group, in this particular dimension, there's no like abstraction from non-trivial bordisms. So you can actually do this, always do this extension. And then you can ask, does it depend on the, by the way, it doesn't work for all groups. So if you ask to go to some other group, you'll have to do something more sophisticated. But for U1 it works, and you can ask, okay, now does it depend on the way you extend it? And it turns out that it's precisely independent if K is, well, if more precisely is if M3, this manifold given a spin structure, and the spin structure is extended to the spin structure here, then K can be an integer.
I know that there is requirement of quantization for non-abelian theory, but for abelian theory there is no, as far as I know.
No, there is one here too. If you believe that you have to be able to define for connection on general principal U1 bundles.
But does that requires compactness of the manifold now?
Compactness of the group, if you want.
What group?
Yes.
Group is U1. The manifold, to make this well defined, M should be, let's take M to be compact. Yeah.
So with non-trivial pi 1 probably, right? Or
Non-trivial pi 1 first one? Well, that's what, of course, underlies. There's a first Chern class here, which labels different principal U1 bundles. That, of course, comes from pi 1 OS 1, and then if you want really the action to make sense, in this generality, for general compact 3-manifold, you have to quantize your K. And there's some further subtlety that related to spin structure. Like if you don't want spin structure, then K has to be actually an even integer. But if it's a spin manifold, then you can show that actually this guy is always even anyway for a closed 4-manifold, and then therefore K can be any integer. So there's some subtleties there. Anyway, the important thing is that these arguments are very distinct. Distinct because in real life, you know, our A is just lives in a trivial bundle because they're not magnetic monopoles, and we don't live in a non-trivial 3-manifold either. We live in a manifold which is Euclidean space times time, right? So this argument seems very suspicious. So, but they seem to work, and then people say, well, this baby TQFT describes that situation over there with integer values of.
The word describes me. I mean, I'm still.
It reproduces. It explains quantization in this way, in this particular case.
So it explains the quantization condition, but it's not that. I mean, I'm trying to understand what is the statement about. I mean, if you look at the upper border, there's like left part and right part. What is the formal connection?
That's actually a good point, and part of the reason I'm not happy with these words is because there's no precise meaning what it means to describe, right? Situation becomes a bit better, or maybe a little worse, I don't know. If you look at this fractional case, in the fractional case, there's more information. This fractional Cohomology phases are not only non-trivial because of this, they're also non-trivial for other reasons. So there are more observables to look at, more observable consequences to look at. And there is some TQFT, which is discovered by, well, it's proposed by Xiaogang and Wen, which is again of Chern-Simons type, which captures these properties. And there's another motivation to say that, well, TQFTs are related to gap systems.
But again, can you maybe say more precisely what captures mean? Because
yeah, well,
it's right now just saying that the quantization condition is saying that just basically okay. That
yeah, so that's a difficult question. But for example,
relation between current and the electric field, that was not trivial, right? You reproduce the relation.
Yeah, right. But to be fair, if you ask what are possible relations you can write down, which don't lead to dissipation, that's pretty much the only one you can write down. So that's not really much of a surprise.
How about edge states?
Okay, but that's the usual primer for TQFT doesn't involve any edges. We just have closed manifolds, so it's kind of difficult to discuss in this language. Now, so the other things you can ask, for example, in the fractional Cohomology case. So the other things beside the fractional value of this conductance, for example, one can argue that the following thing holds. Although, again, that's something not very physical because you cannot really reproduce. So here's a physical thing. So in fractional Cohomology case, it has been argued that there are excitations with fractional charge, and the denominator related to the denominator here. So you can have, say, some quantity which looks like a particle but has charge, like, say, if this 2 pi sigma whole is 1/3, which is actually observed one of the first fractions observed in experiment, then there's some excitations behave as if they had charge, electron charge over 3. So you can show that there's some TQFT which does this for you. Okay, it's fractional electric charge for excitations. So there are more academically. Okay, so this actually has been observed in experiments, but there are more academically. You can look at what happens if you like 2 such guys, and maybe evolve them by moving them around, and this process, if you done adiabatically, gives something independent of the way you move them. And you can also reproduce it from TQFT. But it's true that it's never clear what exactly is supposed to be reproduced, like which features are supposed to be captured. So anyway, and what's worse, at some point became clear that it's not even true that that all gapped phases for no matter have anything to do with TQFT. There are some weird ones which are constructed in the like 10 years ago, so maybe a bit more by now, called fractons. Which have properties so weird that no field theory can capture it at all. So some properties of excitations are so strange that field theory is not going to work. So it's clear that TQFT doesn't describe all gap phases of matter. So I need to cut down somehow, both on the, if you want to make a correspondence, you definitely want to somehow focus on some smaller subset of gapped phases. and maybe also on smaller set of TQFTs, not all of them.
So do you expect that, is there a statement that for a good TQFT you can construct, is there a statement that for maybe some kind of good TQFT you can construct this gapped?
Yeah, the problem is there's no way to go, like, to even figure out, like, somebody has a TQFT, right? Yeah. I can write quite explicitly. How do you go back and construct corresponding lattice model in some sense? Nobody knows, okay? There are some very simple examples of TQFTs for which we don't know.
How do you explain the motivation why you would expect this in the first place?
Okay, let me show you that. Yeah, if you cut down on the both sides, there is a reasonable conjecture which seems to be to verify lots of checks. So, and that's what I'm going to address. And after that, I'm going to forget about TQFT. Just use the TQFT as a black box to make some predictions, and then try to verify them.
Say that since we are considering gapped phases of matter, there's no excitations there's no wavelength excitations, and that's precisely what TQFTs do. They do not have any moving massless degrees of freedom.
Well, that part, yeah, that's true, but topological is much stronger. Having no, like topological field theory is something very fairly, okay, there's no rigorous definition, but there is some quasi-rigorous definition that has a lot of parts to it, which not clear why it should be true for gapped phases. Okay. Also, there's some difficulties in examples. There are some examples of TQFTs which you can just write down, for which, again, there's no, it's not known whether you can construct a lattice model with the right properties, whichever right properties mean.
So you haven't defined what topological is.
Yeah, so topological, I just going to ignore the word topological. That's why I put it in quotes, because what gapped means I know. What topological means I don't know. So let's not even talk about that. Okay. This topological in quotes, it basically comes from some desire to relate to TQFT, which I no longer actually believe in. Not every gapped phase of matter is related to TQFT. However, there is a okay, so there are all these issues. A certain improvement came again about 10 years ago. And there's so the idea is to look at some particularly interesting class of gapped phases. So the idea is due to Kitaev. So this is all in unpublished talks, which you can find on Simon Center webpage if you want to. So invertible phase systems are quite special and maybe have a better chance to relate them to TQFT using homotopy theory. So what do you mean by invertible? Well, for field theories by their sort of the definition, essentially they form sort of a monoid. So you can tensor together field theories and symmetric model operation. And there, okay, so you can do the same thing actually with the phases with systems. So monoidal structure is quite well, symmetric monoidal one. You just have two systems. Just form tensor product of these algebras and just take sort of if you wish, a tensor product of states. That is, on decomposable elements, this new state should be the product of states on each on each factor, and then it's a bounded thing. You can complete it to an actual state on this tensor product algebra. So clearly it's symmetric, and the idea is to look at systems which are in some sense invertible. So what does it mean? Of course, not okay. So we say that A omega is so say prime omega is inverse to A omega if they're composite, but they physically correspond simply like taking one system and putting another one on top of it, sort of, and not having any interactions between them. So if this guy is equivalent in some sense to the trivial system, so to the system that is its same algebra but a trivial state, one of those product guys where you just have unentangled spins. And what does this tilde mean? Well, basically you want to be able to deform this state to this one within some class of allowable states. So it's a homotopy problem. So we need to define a notion of a continuous path of states, and once we define that, we'll have a definition of what this means. Okay. So okay, so that's what we'll call invertible systems. Of course, the inverse is not well defined, but if we define appropriately equivalence classes of states, then at least the equivalence class of the inverse is well defined. So then if you stick with this definition, then your phases of invertible states form an actual abelian group. Okay. So this is kind of proceeds by analogy with K-theory in some sense. It was actually inspired by K-theory because using other methods for systems of non-interacting electrons or fermions, this classification problem actually has been solved in a sense, and the answer is given by K-theory. And this was like a way to mimic what we do in K-theory, but for interacting systems.
So did you say in the beginning you actually have a rigorous definition of all this, but you don't want to give it today?
Not right now, yeah. Okay, so let me just proceed with motivation. So, okay, so there's some definition of this equivalence, or rather, more precisely, just need to define what we mean by continuous, by a smooth, actually, path of states on this sort of algebra. Once it's defined, we'll have defined also this equivalence relation. And
the trivial state again. So,
trivial state is simply the one where this omega naught is simply a product of pure states over all sides. It's called unentangled.
Are you assuming something about A and A prime, or?
They're always of the same type. They're just infinite products of matrix algebras.
They're always infinite.
Well, this uniformly hyperfinite algebras. Yeah.
It's a little bit abstract without some particular example.
Of non-trivial class?
Well, I don't know. If you give some particular example of this monoidal whatever, invertible system.
I'll define I cannot give example until I define what I mean by, say, well, okay, I can give example later. I can define actually what I mean precisely by deformation, but I cannot like give example now. So, anyway, so
basically, because intuitively it looks like you can deform anything to anything, because I mean,
yeah, but that's
there's an element of some vector space, so
no, you're not deforming states. We're deforming states with some additional structure, and we need to deform within states which have this structure. So I'll explain later which structure I want to impose. Yeah, in the case of free fermions, one can make very concrete because in the case of fermions, non-interacting fermions, these states can be just described by projectors in some one-particle Hilbert space, and then there's nothing to it but just deformation of projectors. Say in the case of a fermion just hopping on a lattice, the translation invariance, that state is just described by a projector-weighted function, smooth function on a torus of dimension d. So in this homotopy deformation, simply deformation of this within the class of smooth projector-weighted functions. So that's exactly topological K theory of a torus. Okay, so in that case, it can make concrete. So anyway, why focus on these guys? Because they're much less interesting, actually. Well, actually, they're interesting, maybe less interesting physically, but well, physically, actually, they have some interest too. They're called topological insulators. In some version, they're called topological insulators. But the key point is this. So Kitaev argued non-rigorously because, well, he argued that there's some way to define the space of all such systems in dimension d, some infinite dimensional space.
Sorry, what is dimension here in terms of A? Is it?
That enters, well, okay, the algebra A, by the way, doesn't depend on dimension at all. It depends on the list of dimensions of this matrix algebra. For example, you can take all of them to be 2 by 2 matrices. And then it doesn't matter what the dimension is, you get they're all isomorphic. So all these UHF algebras are all isomorphic. So D, though, enters in the definition of which states you're interested in and how to define equivalence relation. So, so dimensions enters only in the level of states and equivalence relation. So the algebra itself depends only on the list of dimensions of your individual factors. Anyway, so Kitaev argued very non-rigorously that there's some space of xd of invertible systems, lattice systems. They're all gapped by sumption, actually. And moreover, well, it has each of them has a base point, which is a sort of trivial system. And he argued that the loop space, base loop space of xd is actually homotopy equivalent to xd minus 1. So the collection of all these spaces then forms a, it's called omega spectrum. So that is true, actually, apparently, in the case of non-interacting fermions. And by analogy, he guessed that's going to be true in the interacting case. And he even gave some hand-waving argument how to construct homotopy equivalence. So again, I'm not going to describe this because it's very hand-waving, but there are some arguments. Actually, the map from in one direction actually doesn't involve invertibility, but the map of the opposite direction uses invertibility crucially. Okay. So because of that, if you're interested in, say, phases, well, so set of phases in the dimensions is just pi naught, so in the dimensions. Pi naught of xd, but because of, so to each spectrum you have associated generalized cohomology theory, and because of this it's the same as called, say, reduced cohomology theory called hx of degree d over point. Okay. So we have some, so according to Kitaev, if you want to classify all invertible topology, all invertible phases in all dimensions, you just need to figure out which spectrum or generalized cohomology you're dealing with, and then you classified all the phases in all dimensions.
I'm confused. So how can this be done? So you're saying the set of loops. So I'm not sure I know what is loop.
Yeah. So you look at just continuous maps from a circle to your x, which begin and end. The marked point on a circle maps to your marked point on x. Such space can be topologized, get some horrible infinite dimensional space, and but it can be well defined for any topological, for any, say, CW complex, and that's also actually CW complex. The loop space of CW complex is a CW complex too. And then you can say, well, you can ask, well, and then that means it's the homotopy equivalent. So
is it kind of intuitively obvious that if you know this relation, then you can reconstruct the relation below, or is it?
No, it's not obvious. It's a non-trivial. Well, you can look up, say, in Hatcher. It's not very non-trivial, but it's somewhat non-trivial that to construct, that every omega spectrum gives rise to some cohomology theory.
Sorry, and XD is the space of all invertible systems.
Yeah. What does it mean? I don't know. You cannot fix an algebra in that case. You have some sort of limit over all algebras or something.
So like points of XD are different type. Every point of XD.
Yeah. So how to define XD? I still don't know.
But somehow, this way of argument says that you somehow you want to study the systems of deformation, right? Because you want to do homotopy theory, so that means that you kind of.
Yeah. So in these lectures, I'm going to try to probe the topology of XD by at least defining what it means to have a map, continuous or smooth map from some finite dimensional manifold to XD. So that I can define. Okay. So I don't know what XD is. In some sense, it's as defining XD. There is some notion of a.
You want to define family of invertible systems.
Yeah. So once I know, okay, in some sense, it's like defining XD. There's some approach to infinite dimensional manifolds called topological space, which basically defines infinite dimensional manifold as a pre-Schiff on side of manifolds. So basically, concrete presheaf. So basically, look at just define set of what it means by to have a smooth map from a finite dimensional manifold to that guy, and you define for yourself that infinite dimensional guy.
So, but they haven't actually defined what an individual system is. So.
Well, I'll define individual systems. But anyway, so that's the proposal. It says, well, if you somehow if you believe in this and somehow manage to guess the spectrum or figure it out, or generalize cohomology, you actually solve the classification problems, at least for invertible states. Interestingly, when he proposed that, I sort of said, okay, well, there is some very nice cohomology theory called cobordism. So how about that? So let's try to use that. Well, it's more like a dual of cobordism in some sense. So I propose that in some cases you can sort of identify it. Maybe I said, maybe I should say that this is just the Pontryagin dual of a bordism of M. So, okay, so that's not quite right because this doesn't form a generalized cohomology theory, but it had some tweaks to make it work. But then Fried and Hopkins simultaneously looked at invertible TQFTs. And they showed, with some assumptions, that invertible TQFTs are also classified up to homotopy by cohomology groups of some spectrum. And that spectrum actually, again, it's not bordism spectrum, but it's some closely related to it. It's called Anderson dual of the bordism spectrum. So let me just say. Okay, so invertible are classified up to homotopy by So now again, this result is not completely like hypothesis free because they worked in this framework of Lurie where you're supposed to look at functors from some infinity category to not infinity category, and they need to choose some target category, and they guessed what the right target is for the invertible case, and then they were able to do classification. And the interesting thing is that in the case when, say, so in the case when this group is actually torsion, that's literally the same as that. And and then if you look at physics literature and look at all the proposals for what the classification is in a given dimension, then you'll find that actually it seems to agree in all cases that I've seen with this result. So it looks at least for invertible TQFTs, you should be able to make connection with the invertible gapped phases. So that's so that's the current hypothesis, which are called the refined Kitaev conjecture. Okay, so the homotopy equivalent. Okay, so now, okay, so this is all motivation. Now,
are we going to use this invertible TQFT in this course?
No. It's a relief. Okay, so, however, so let's see. So I would like to check consequence. Okay, I don't know how to prove this. So Nikita has some ideas, but he's been reading Lurie diligently. I haven't. So let me just. I'm going to explain how to check some consequences of this conjecture, of this refined KTF conjecture, and actually more generally, some of the construction I'm going to discuss also work for not just for invertible phases, but also for general gapped phases. So it gives you some clue about what to expect for the space of all gapped systems. So, but let me just look at the invertible gap, because in that case we actually have a sharp prediction because of that. So predictions for XD. So in low dimensions. So just homotopy type, of course, not actual space. Well, in 0 dimensions, it's kind of obvious anyway. So in 0 dimension, you can just say, well, what is the space of all states? In that case, locality plays no role. Just the space of lines in an infinite dimensional Hilbert space, probably your model for that space. And that's, as far as homotopy theory is concerned, it's what's KZ2. It's a I remind you that K, G, N is a space which is uniquely defined by the following condition, that pi n is equal to G and pi m is trivial. So so these are these famous Eilenberg-MacLane spaces. And for 0, it's just space of lines in the Hilbert space, which is actually has type, well, it can take CP infinity or KZ2. Like by the way, the fact that it's connected means there's only one, the trivial phase, kind of obvious anyway. In 0, nothing interesting happens in 0 dimensions. But this still has interesting topology, so we can discuss that later. Now, in the 1 dimension, again, there are no interesting phases according to this prediction. There's only one phase of lattice systems, the trivial one. But there's even more interesting topology. There's non-trivial degree 3 cohomology. So, and that's actually one of the things I want to discuss, how to see that at least. So in dimension 2, supposedly we have a KZ4 times Z.
Since this K appears so often, can you say something more about this? Because
Okay, so not much to say besides this. It's a homotopy type. It's any space with this kind of homotopy groups. There's some infinite dimensional spaces with. I can draw KZ1. Example of a KZ2 is a CP infinity. Sort of a limit CPN. You can just say it's embed CP1 to CP2 and so forth, take it like a limit, and then you get something called CP infinity. You can also say, think of it as a space of just lines in a Hilbert space.
Isn't it already what you're writing contradicts your statement that loop space of XD is the same as XD minus 1?
No, that's actually the homotopy equivalent.
KZ3 is omega of KZ4, but you say times Z.
So you look at base loops, right? So the
components are the same, right?
yeah, so you pick a if you map some base point to a base point, it should say in zero at some point here. So you just get loopsons here. Okay.
So then how can you know that it is times Z if your theory is just knows only about base spaces?
No, I'm saying this is a prediction for this spectrum, which is Anderson dual of Tom.
What, on your homotopy theory or on something else?
Yeah, this is, you can, it's Anderson dual of the audience board is what I'm displaying here. This is what I'd like to check. Okay. So
I can ask a question.
Yeah.
So for example, in dimension 0, saying that this thing is connected, but it's a KZ2, is it saying like for every like two-dimensional path of state, like family of states, you have some kind of invariant?
Yeah, I'd like to check that. Yeah, so in dimension 0, that's a well-known fact described by Michael Berry, that if you have a family of zero-dimensional quantum mechanical systems with a unique ground state, then you naturally get a degree 2 class on the parameter space, which is a pullback of that class here. And that class is just the first-order class of the line bundle of ground states. So that we understand. And then the next question would be, okay, can I just understand where is degree 3 class? So the prediction is that you have a family of one-dimensional lattice systems. Then you should be able to construct pullback of that class here, which is degree 3 class, on the parameter space, which is like a Berry class, but it's in the wrong degree, it's in degree 3. Okay? So some sort of gerb. So which is the higher analog of a line bundle. So first question is, okay, can you construct a gerb of 1D systems? Okay, so
maybe another question. So like this ring has a product, right? The cohomology ring.
Yeah.
What is the product in terms of these?
Well, there's no particular. Yeah, I don't see any interpretation. This is purely as a billion groups, and no like product that I care about here. I just want to classify phases or maps or families of systems. I don't take products here, just as a billion groups. Yeah, by the way, so this tells you that if you decided to work in low dimensions, there's no phases, but I can get something interesting if I map if I consider families of systems, not just pi naught or whatever. Okay.
Could you just for simple-minded people just translate this into like you have a zero-dimensional physical system, system. So what is predicts actually? So what is KZ2? What?
Well, just the physical meaning is this. Like when you actually the way they bury. Okay, so here's some 2 minutes of comic relief. So I would have done it later anyway, but if you're asking, so I can do it now.
Or Berry phase or what?
Yeah, Berry phase, or more precisely Berry.
Some singularity in the parameter space. Well, some particular type of singularity.
So, so people who studied molecules were interested in the following problem. They wanted to sort of solve first for fix a position of nuclei in a molecule, then solve for ground state of electrons, and then get some sort of effective description for nuclei. And then, well, naturally we think, okay, well, there's some kinetic energy and potential energy. Potential energy comes from these electrons. And if you can figure it out, you're done. Well, it turns out that's actually not quite true. It turns out that also on the parameters, well, the space of parameters in this case is just position of nuclei, right? So, and okay, you generate sort of potential in that parameter space, but you also generate a connection. So in general, your wave function actually not function on this parameter space, but a section of some line bundle. And at first, it wasn't even noticed. There was something fishy going on, but nobody paid attention because these systems are, in this case, your wave function was real. So they're not non-trivial Chern class. There's a mod 2. There's a mod 2 class. There's a first Stifel-Whitney class, but physicists are like sloppy with -1s, so they didn't pay much attention to that. So so your wave function in general is some wave function. It's a section of some trivial line bundle with a holonomy like just ±1. And then Berry was the first to look at similar questions for systems which don't have time reversal invariance, and then your wave function is complex. And he noticed that your, say, effective action for the system of ions, well, there's a usual term, kinetic energy. There is a potential energy. Or something more complicated, maybe not pairwise, just some function of this R's. Just some function of all the coordinates. Plus, there's also a term like with a single time derivative.
Magnetic field.
Sorry?
Just vector potential.
Yeah, vector potential, yeah. So you have something like this also. So the kind of action you get in general if you don't have time reversal invariance. And so this connection here, this gauge field, is referred to as the Berry connection. But it was in particular, it has a curvature. In this case, M, what is M? Well, M is a space of configurations of points in R3, so n points. So we have some non-trivial topology there. Moreover, sometimes this closed 2 form can have non-trivial de Rham cohomology class. So that also happens, and that's what's known as a Berry class. So and actually, it lives in integral cohomology. Can live in integral cohomology. So it's called the Berry class. And the fact that cohomology of this KZ2 is just all comes from just powers of this single class in degree 2 means that the Berry class is the only interesting class. And there's nothing else you can construct. There's no other topology which effective action can detect for zero-dimensional systems. So, okay, that's a story of the Berry class. And interestingly, once you go into higher dimensions, it looks like the analogs of that are going to live in ever higher degrees. Okay, so now it's a bit non-trivial. Okay, so in dimension 1, you expect to get degree 3 class, integral 1. In degree 4, you can have, well, you have this just several different types of systems, but for any particular one, you get a degree 4 class and so forth. And say here, you get, you can guess, KZ5. Well, times KZ1, which is S1. Starting from dimension 4, it's not so easy to describe the space because it's not just a product of these building blocks. It's some non-trivial fibration because you get what's called known as Postnikov invariant. So then let's not worry about that. So.
But now this is connected, right? It's cannot.
Now again, there's no phase. Yeah, but in dimension 4, there is actually two different phases. So it's a call from Bordism. So all these things, these guys can be related to some Bordism groups. This is not in a very particular simple manner because not really Bordism which we care about, but this Anderson dual of the Bordism. This Z has to do with first Pentragian class, basically. But that relates to Bordism in degree in dimension 4. So Z2 here has to do with the fact that you have non-trivial class like this for 5-dimensional manifolds, a second times third Stifel-Whitney classes. So it's again, it's a generator of Bordism group in dimension 5. So now, so ideally, we would like, as a start, to construct at least one system in each equivalence class of these guys. Say, in dimension 2, you can construct non-trivial system in each class here. In dimension 4 spatial, we can construct a non-trivial system here, and so forth. We still don't know how to do that, by the way. But one can, what one can do more easily is to construct analogs of these Berry classes. So namely, look at the families of systems and construct pullback of these classes on the target. That we can do.
Berry classes is just a magnetic field, as far as I understand.
No, it's just a sort of effective magnetic field in the parameter space.
Yes, I understand. So that's what you call a Berry class.
Yeah. So the cohomology class of that. So in higher dimensions, by the way, we'll be just happy constructing the class because actual computation of, there's not like canonical definition of a connection, like analog of connection in higher dimensions. So we'll just be happy with constructing the class itself. Not concrete 3 form or the 4 form realizing that. Okay.
So why did you say comic relief? So is there some famous molecule where this is important?
Well, the comic part is that, first of all, for like 30 years, people did computation, never noticed there's something fishy. Like,
well, maybe it's just that it's not important.
It is important, but...
did they make a mistake in some calculation?
Well, there are applications in optics. And before Berry, there was some Indian guy with a very complicated name, which I've forgotten.
Yeah, they also, Berry came from atomic physics.
Applications in quantum field theory, which I can discuss, but probably not here.
Yeah, and then Berry also didn't understand what he got either. So that required a mathematician, namely Barry Simon, who actually, probably one of the most cited papers is just explaining that, if you have a closed 2 form, then its periods are quantized because it's the first Chern class. So So it was like Simon actually explained that there's actually some non-trivial topology going on there, and like Barry didn't realize that. Anyway, so let me just say a few words. So we want to construct these classes. Also, another thing you can do besides looking at families of systems, which is a bit. Oh, by the way, so still don't know how to construct. There should be some invariant attached to two-dimensional systems, which gives you this integer here. I would love to be able to construct it. I don't know how to do that. That somehow is tied to the first Pentragian class, which is a very mysterious thing too. So, but I can do some other things besides families. Predictions for systems with U1 symmetry. That's motivated by this quantum Hall effect problem. So here I'm just going to list the pi naught of the spaces.
This is what we would call like symmetry protected.
Yeah, right. So you can. So formally, it's actually not okay. So there are predictions you can get from these guys too, and the reason you can get them without knowing anything else is because formally, a system which is invariant under the action of some group is like a family of just systems parameterized by the classifying space of the group. So if I want to say no, what is the pi naught of xd u1 is the same as this generalized cohomology group of degree d of the classifying space of u1, which is actually the same guy as before, as we already see, kz2. Wait. So if I know this cohomology, if I know that table there, I can also compute this in principle. So, and that gives. Sorry?
I don't understand. You have some very powerful way to derive classification for symmetry protected phases from classification.
Right. It's like, well, no, from knowing this actual homotopy type of spaces. Just knowing pi naught of the space is not enough. But if I know the actual spaces up to homotopy, then you can formally treat a symmetry G as just a base of the parameter space, which is BG. So I'm not going to use it. When I'm actually going to construct some of these things, I'm not going to use this viewpoint, but just telling you that's how we can get predictions at least. So say in zero dimension you get Z, one dimension you get nothing, two dimension you get Z plus Z. Well, one of the Z's is just from there, but the other one comes from U1 symmetry. In dimension 3 you get nothing again. So well, in dimension 4 you get some factor of Z. Anyway, so this second Z is actually this guy which appeared in integer quantum Hall effect. That 2 pi times sigma h is that integer, supposedly. So if we know how to associate to any two-dimensional system with an energy gap and U1 symmetry this invariant here, we also figured out why Hall conductance is quantized, basically. Okay. All right, so that's the motivational part. So I can stop here, or I can begin the more rigorous part. So what are the preferences? Can go for another 15 minutes if you want.
We didn't take a break.
So okay then.
So we could go for 15 minutes easily.
Okay.
Yeah. If you
sure. Yeah.
feel fresh.
No, it's fair. Okay, let's start like talking about what actually. Let's set up the problem. Let's forget about this TQFT stuff. Let's use this just a black box. There's an oracle, Kitaev or Frieden Hopkins or whoever, who made predictions about classification of phases. Then we want to check them for some construct this invariance actually. So let me first begin by setting up the traditional setting for lattice study of quantum lattice systems. Okay. So I already said some of these things. So we have, first of all, uniformly hyperfinite C-star algebra. I'll just say that there's some subset of Euclidean space of dimension d, and I take product and take completion. With respect to what? Well, Aj is a matrix algebra of some size. So this is finite dimensional. And therefore C-star algebra, so it has a norm. So I take a product, I get a norm star algebra, and then, well, it's not complete, but I can take completion, it gets a C-star algebra, which, look here. Okay. So now what is a C-star algebra? Well, maybe, I don't know. I should say it, well, it's first of all a Banach space. It's a Banach space. You have compatibility with the multiplication. You have compatibility with the star structure, and you have a C-star identity. So we have all these things, and then given
what's the norm on A in terms of norms of on AI?
Norm on A. Well, it just for any finite element, say before a complete element here is simply a finite product of matrices, right? So it's just one big matrix algebra. Okay, so that norm is the norm I'm using. So. So now, the nice thing about C-star algebras is that you can show that, well, the notion of a positive element so some guy A, this algebra, such that, first of all, it's self-adjoint, and the spectrum of this element is non-negative. So, and the interesting thing is that these guys form, well, not entirely obvious that they form a cone. So there's a cone of positive elements, and then you can define as so a positive linear functional. So positive elements. So A plus, say, is a set of positive elements. So it is positive if it's the case, and if you normalize it in addition, you call what's called a state. So identity. Well, all our algebras are unital, so we just say that if you normalize it, then this thing called a state on this guy. Okay. Now given algebra and the state, by the GNS construction, you get a representation on some Hilbert space. But in reality, it turns out that it's good to know it's there, but in all manipulations we're going to be doing, we're going to avoid work in Hilbert space and going to work entirely in terms of C-star algebra. So that simplifies life a lot. So in particular, well, so I don't need to think about any like weird topologies, like weak topologies. Everything's done entirely within the C-star algebra. So now the last thing we need to specify is time evolution. So I want to define at least what gapped means more precisely. So time evolution so we have So it's the same given by one parameter strongly continuous group of automorphisms. That is, you have some for any real time, you have a homomorphism from A to itself. Well, it's an automorphism which preserves the star structure. And satisfies this. Well, and also it's strongly continuous, meaning that if you act on a particular element, this is a continuous function of t. Okay. So that's standard setup. So before I talked about Hamiltonian, well, one can, so next thing I want to express is that first of all, my state is, okay, so and I want, of course, so first of all, so I want to say that omega, write down a condition that omega is a gapped ground state of the corresponding Hamiltonian. But actually it turns out, well, Hamiltonian sum is an operator in Hilbert space. It turns out I don't need to actually go to Hilbert space, I can write everything down in terms of this C-star algebra. So, so what else can I say? Okay, so, first of all, you can define a derivation like this. So this, so okay, if it's defined, it defines the derivation of the algebra. You know, all the derivation you get physically from normal behaving time evolution, they're all unbounded. So delta is only defined on some dense set. It's a derivation. Okay. Some dense subset of this guy. Depends on your delta. Huh? D of delta. So each derivation you get from automorphisms, they each have their own domain. Okay. And that's actually one that causes a lot of problems because if you, like in quantum mechanics, when you're dealing with evolution or symmetries, well, their generators are derivations too, but they're bounded derivations. They form a Lie algebra. So in the quantum C-star algebra as well, like the domain of Hamiltonian, of energy of time evolution, I would say this is a Hamiltonian. If alpha t is the time evolution, this is a Hamiltonian. So from the point of view of infinite volume, so it is D is the Hamiltonian. Okay. And you have some other symmetry, not time evolution, say, I know, electric charge, some U1 symmetry. That it also has a corresponding derivation, which is the charge. And then naturally, the question arises, well, do your symmetries form a Lie algebra? And then it becomes a tricky question if you're not sure that they all have the common domain. And it turns out that there is actually physically interesting derivations. They all have the same large and interesting domain, and we're going to get to that later. So you can actually essentially make everything algebraic once you realize that.
Can I ask a question? So should I think physically that delta acts on elements of the algebra by commutation?
Yeah, so let me just say that. So I'm not going to say it rigorously for now, but it's clear that physically interesting ones, so physically interesting derivations all have the following form. where, so some infinite sum, then of course you need to worry, like when is this convergent? So you need to put some constraint, but that's how physicists think about Hamiltonians. They just have its collection of sort of energy density for each side, right? And then, but then you need to say exactly what you require from them, so that this actually does have a dense domain. And that's actually, physicists would not start with time evolution, because who knows what time evolution is? A physicist will start with actually with derivation. And then you would ask, okay, can I exponentiate it to actual evolution? And again, in general, it's a thornic problem, but if you have a nice enough collection of these densities of energy, that can be solved once and for all. There's something called Lieb-Robinson bound, which takes care of that, which guarantees that you can exponentiate some class of derivation. That's what we're going to use heavily. Okay. So all these problems have a solution once you restrict to a sufficiently interesting, nice class of Hamiltonians or evolutions.
So you're saying that it can be integrated?
Yeah. So there's actually, yeah, so there's a way to reconstruct. For a class of derivations, you can reconstruct evolution. Okay. So, okay, so then finally I just want to state what the gap means. So first of all, what's a ground state? So omega is a ground state for delta if you have the following thing. So that's a notional ground state. And if you write in terms of this generalized representation, that just literally means that energy of the states are, well, the way it works, the energy of the state omega is 0, but then this condition means that all other states have energy which is non-negative. Okay. And, well, the spectrum of Hamiltonian in Hilbert space is non-negative. But so omega is called gapped with gap greater or equal than some number if is a stronger thing, you can say and if you write in terms of generalized representation corresponding to the state omega, you'll see that what it means that, first of all, the state omega is the unique state with 0 energy, and second, that all other states have energy at least delta. So incidentally, so okay, so in particular, if you have, say, two different Hamiltonians, two different deltas for which omega is a ground as a gapped ground state, is a gapped ground state for delta 1 and delta 2 with gaps delta 1, delta 2. Then it is also, so then it also gapped with respect to this. Okay, so where and the gap is that. Just follows from this condition. So we see that for a given state, the space of Hamiltonians which are compatible sort of with it, so it's gapped, is contractible. So when we consider homotopy theory of states, we should be able to forget about the Hamiltonian because it's just a homotopically trivial set anyway. It's a convex set. So yeah, so I'll stop here. So this set up the problem, and next thing I want to describe more precisely which class of derivation I'm going to be working with, and how to extract some algebra and some deformation theory out of these derivations.
So you mentioned, you gave first examples of gapped states. integer quantum Hall effect, fractional quantum Hall effect. But then you also said, you mentioned this invertible states. So which of the ones that were gapped are invertible and which are not invertible?
Well, integer quantum Hall states are invertible. And those can be realized by non-interacting fermions, for example. You can find states in that phase which are non-interacting.
The fraction.
Fractional is all but essentially all non-invertible, and actually there's no construction even of a single state which has fractional quantum Hall conductance, strictly speaking. So it's all what's an experiment, and there's some guesses that there is some Chern-Simons field theory. But if you ask, okay, is there any model which gives that fractional Hall conductance? Lattice model. Well, actually, Nikita wrote some model like that, just like half a year ago, my student. But it's a bit weird. It uses vertex operator algebras, so it kind of reverse engineers something. So another hallmark of quantum Hall states is that fractional ones. That there is a conformal field theory of edge modes living on the boundary. So you can sort of reverse engineer a lattice model starting from vertex operator algebra of those modes. But that ends up being not in this class of systems, because on each side you have actually infinite dimensional space of vertex operators. So doesn't fit into this framework yet. There's no construction with finite dimensional on-site Hilbert space for these fractional quantum Hall states.
I also had another question. So there's something here that I don't understand, because often people, I thought, people wanted to classify not states but Hamiltonians. For example, to say that two Hamiltonians are equivalent provided that you can connect them by a path which doesn't close the gap.
Yeah, it's difficult to control this. What do I mean to deform so that it doesn't close the gap? It's much easier to...
Well, why is it? Well, it's difficult to control, but the definition perfectly makes sense.
Yeah, all I'm saying is that in reality you don't need to know the Hamiltonian. It's easier to think in terms of states with some Hamiltonian, which you don't really care about too much. So, for example, you can show that if I define some notional equivalence between states, which guarantees that if one of them is gapped, this has a Hamiltonian, you can actually construct a family of, the notion of a family of gapped, a family of states, such that if any point in the family has a gapped Hamiltonian, then all of them have it. So, and it's horribly complicated Hamiltonian, but I don't need to know anything about this. So, to a large extent, notion of gapped is only needed to prove some structural properties of the state. You don't need to know the Hamiltonian. But you can show that it exists. Like if you have a family of states, the notion of a family is constructed in such a way that if any particular state has a Hamiltonian with an energy gap, that all of them have a Hamiltonian with an energy gap. Not a unique one in any sense, but you can construct it. You sort of parallel transport it.